In the deepest laboratories on Earth, scientists have discovered something that defies every rule of reality we thought we knew. Particles that remember the future, information that travels backward through time, objects that exist in multiple places until someone dares to look. These aren't science fiction nightmares. They're quantum paradoxes that have left brilliant minds questioning whether reality itself is an illusion. A single photon of light approaches two narrow slits cut into a metal barrier. You might think this is simple. The photon goes through one slit or the other. But when scientists fire individual photons at these slits, something impossible happens. Each photon somehow passes through both slits simultaneously, creating an interference pattern on the screen behind. This defies logic. A particle cannot be in two places at once. Yet there stands the evidence, bright and dark bands that only appear when waves collide with themselves. But here comes the truly disturbing part. The moment a scientist places a detector at one of the slits to catch the photon in the act, everything changes. The interference pattern vanishes. The photon suddenly behaves like a normal particle again, going through just one slit. It's as if the photon knew it was being watched and decided to stop its quantum trickery. If particles change their behavior based on observation, what does this mean for reality itself? Were the photons always going through both slits, waiting for us to force them to choose? Or do they literally exist in multiple states until measurement collapses them into a single truth? Light has been playing a cosmic game of hide-and-seek with physicists for over 3 centuries, but quantum mechanics revealed something far more disturbing. Light doesn't just behave like a wave or a particle, it literally becomes whatever the experiment is designed to detect. Set up an experiment to catch particles, and light arrives as discrete photons. Design an experiment to measure waves, and light transforms into rippling electromagnetic fields. But here's where reality starts to break down completely. Light makes this choice based on what you're planning to measure, even before the measurement happens. Scientists can prepare light in one configuration, then change the detection method at the last possible moment. Somehow, light already knows what's coming and adjusts its behavior accordingly. This isn't just academic philosophy. Technologies like lasers, LEDs, and solar panels all depend on controlling light's wave-particle nature. We've built our modern world on a phenomenon we don't understand, harnessing a quantum mystery that challenges the very concept of objective reality. Deep in a physics laboratory, a photon begins a journey that will challenge everything we understand about cause and effect. Scientists split a single photon into 2 entangled particles that remain mysteriously connected regardless of distance. One twin heads toward a screen that will record whether it behaved as a wave or particle. The other travels to a distant detector, where researchers can choose to either preserve or destroy information about the photon's path. Here's where time itself starts to break down. The first photon hits the screen and creates its mark before the scientists make any decision about its twin. According to common sense, the pattern should be fixed, but quantum mechanics operates by different rules. Hours, days, or even years later, when researchers finally examine the distant twin, their choice retroactively determines what the first photon did in the past. Scientists have stretched this effect across enormous distances. They've sent photons on journeys spanning hundreds of miles, with detection choices made on different continents. The correlation remains perfect. A decision made in Tokyo instantly affects a photon that arrived in New York hours earlier. The most unsettling version involves astronomical distances. Imagine a photon from a distant quasar traveling billions of years through space before reaching Earth. According to quantum eraser experiments, our decision today about how to measure this photon can retroactively determine whether it behaved as a wave or particle during its billion-year journey across the cosmos. This isn't theoretical speculation. Multiple laboratories have performed these experiments with consistent results. The future genuinely appears to influence the past at the quantum level. John Wheeler proposed an experiment so disturbing that it took decades for technology to catch up with his vision. A photon approaches a beam splitter and must somehow decide whether to take one path like a particle or explore both paths like a wave. But the scientists don't configure their detection equipment until the photon is already committed to its journey through the apparatus. When researchers finally performed Wheeler's delayed choice experiment, the results were exactly as terrifying as he predicted. The photon's behavior depended entirely on choices made after it had supposedly already traveled through the system. Configure the detector to look for a particle, and the photon retroactively becomes a particle that chose just one path. Set up the detector for wave behavior, and evidence emerges that the photon explored both routes simultaneously. Wheeler extended this concept to cosmic proportions. Consider light from a distant galaxy that passes around a massive star on its way to Earth. According to delayed choice logic, we could set up an experiment where our measurement today determines whether that photon took one path or both paths during its million-year journey through space. This suggests that consciousness might be reaching backward through time to edit the quantum history of the universe. Every observation we make could be collapsing wave functions that existed long before Earth formed. In quantum mechanics, the act of observation doesn't just change what you see, it literally creates what exists. Consider an electron spinning around an atomic nucleus. Before measurement, this electron doesn't have a definite position or velocity. It exists as a ghostly cloud of probabilities, simultaneously occupying multiple locations and states. But the moment you try to detect where the electron actually is, something catastrophic happens. The entire probability cloud collapses into a single point. All those potential positions and velocities vanish instantly, leaving behind just one definite outcome. The electron suddenly becomes real in the classical sense, but at the cost of erasing every other possibility that existed moments before. The implications reach far beyond laboratory experiments. If electrons collapse into definite states only when observed, what about the atoms in your body? Are they existing as probability clouds until some form of consciousness detects them? Some physicists argue that observation requires conscious awareness, that human consciousness literally creates reality through the act of perception. Others propose that any interaction between quantum systems counts as observation, but neither explanation resolves the central mystery of why reality appears to need outside intervention to become definite. If reality doesn't exist until observed, what was the universe doing for the billions of years before conscious observers evolved? Were galaxies, stars, and planets existing as vast probability clouds, waiting for someone to look at them? Eugene Wigner created a thought experiment that splits reality in two. Imagine your friend locked inside a completely isolated laboratory, performing a quantum measurement on a spinning particle. From your friend's perspective, the measurement has a definite outcome. The particle is spinning either clockwise or counterclockwise. But you're standing outside the laboratory. Since you can't see inside, you must treat the entire system, your friend, the particle, and the measurement apparatus, as a single quantum entity. From your perspective, everything inside exists in superposition. Your friend is simultaneously observing a clockwise spinning particle and a counterclockwise spinning particle, existing in both realities at once. Your friend experienced one definite outcome, but you're describing them as being in two contradictory states simultaneously. Both of you are using quantum mechanics correctly, yet you're reaching opposite conclusions about the same event. Modern experiments have created scenarios where multiple observers make measurements on entangled quantum systems, leading to contradictory but equally valid descriptions of the same physical events. Each observer's quantum mechanical calculations are mathematically correct, yet their conclusions about reality are incompatible. At the heart of quantum mechanics lurks a problem so fundamental that it threatens to unravel our entire understanding of reality. Quantum mechanics describes particles as wave functions that evolve smoothly and predictably according to the Schrödinger equation. But then something catastrophic happens during measurement. The wave function undergoes what physicists call collapse, an instantaneous transformation from multiple possibilities into a single definite outcome. This collapse violates the very equations that make quantum mechanics work. The measurement problem asks, when, where, and how does this collapse happen? If wave functions follow deterministic equations, what causes them to suddenly become random? If quantum systems exist in superposition until measured, what qualifies as a measurement? Scientists have proposed dozens of solutions. Some argue that consciousness causes collapse. Others suggest that large systems automatically become classical through interactions with their environment. Still others propose that wave functions never actually collapse, but instead branch into parallel realities where every possible outcome occurs simultaneously. The most disturbing possibility is that measurement doesn't solve the quantum puzzle at all. It just pushes the mystery one level deeper. Every detector designed to observe a quantum system is itself made of atoms that should follow quantum rules. When a particle detector clicks, what causes the detector's own wave function to collapse? Quantum superposition sounds harmless in textbooks, but its true implications are the stuff of nightmares. The standard explanation makes it seem almost mundane. A quantum particle can exist in multiple states simultaneously until measurement forces it to choose. But consider what it feels like to be in superposition, not the particle, but you right now. Quantum mechanics suggests that the atoms in your brain exist in countless overlapping states. Your neurons are firing and not firing simultaneously. Every synapse is both active and inactive until some form of measurement collapses them into definite configurations. If consciousness emerges from brain activity, and brain activity is quantum mechanical, then your thoughts might exist in superposition too. If superposition applies to large-scale objects, then entire cities might exist in multiple configurations simultaneously. Buildings could be both constructed and demolished. People could be both alive and dead. The entire planet could exist in a superposition of every possible state it could occupy. Scientists have successfully created superposition states in increasingly large objects. They've put molecules containing hundreds of atoms into superposition. They've made tiny mechanical devices that vibrate and don't vibrate at the same time. Each experiment pushes the boundary between quantum weirdness and everyday reality a little further. Schrödinger created his famous cat thought experiment to show how ridiculous quantum mechanics becomes when applied to everyday objects. A cat sits in a box with a Geiger counter connected to a hammer poised above a flask of poison. When the Geiger counter detects radiation from a decaying atom, the hammer smashes the flask and kills the cat. Until someone opens the box to check, quantum mechanics insists the atom exists in superposition, both decayed and undecayed. Therefore, the cat must be both alive and dead simultaneously. Schrödinger intended this as proof that quantum theory couldn't possibly apply to macroscopic objects, but subsequent developments in quantum physics have made the cat's predicament far more plausible and infinitely more terrifying. Scientists now understand that there's no fundamental barrier preventing large objects from entering superposition. This means your neighbor might literally be both alive and dead right now, existing in quantum superposition until you knock on their door to check. Every person you haven't seen recently exists in a ghostly state of overlapping possibilities. Your coffee mug sits on the table in superposition, simultaneously full and empty, hot and cold, even broken and intact. If consciousness causes quantum collapse, then unconscious people might remain in superposition indefinitely. Everyone who's sleeping in a coma, or simply not paying attention could be stuck in quantum limbo, existing in all possible states simultaneously. Albert Einstein called it spooky action at a distance. When two particles become entangled, they form a connection that transcends space and time. Measure the spin of one particle, and you instantly know the spin of its partner, regardless of how far apart they've traveled. Before measurement, neither particle has a definite spin. They exist in an entangled superposition, a single quantum state that describes both particles simultaneously. Even when separated by millions of miles, the system remains unified, as if space itself doesn't exist at the quantum level. When you measure one particle and find it spinning clockwise, the other particle doesn't just happen to be spinning counterclockwise, it becomes counterclockwise at that exact moment. The measurement on Earth instantly affects the state of its partner orbiting Jupiter. Scientists have tested this spookiness across increasingly vast distances. They've entangled particles separated by hundreds of miles, confirming that the connection remains perfect regardless of space. The universe genuinely appears to support instantaneous connections between distant objects. Some physicists propose that entanglement reveals the true structure of reality. Rather than separate objects interacting across space, we might live in a single unified quantum system where the appearance of separation is just an illusion created by our limited perspective. Einstein couldn't accept that quantum mechanics painted a complete picture of reality. Together with colleagues Podolsky and Rosen, Einstein devised what they thought was the perfect argument against quantum mechanics. The EPR paradox described two particles with correlated properties sent in opposite directions. If quantum mechanics was correct, measuring one particle would instantly determine the state of its distant partner, requiring information to travel faster than light. Then John Bell developed a mathematical test that could distinguish between Einstein's hidden variables and true quantum entanglement. Bell's theorem showed that if hidden variables existed, they would produce correlations that obeyed specific statistical limits. Quantum mechanics predicted correlations that violated these limits. When scientists finally performed Bell's test, the results were devastating for Einstein's worldview. Quantum correlations exceeded Bell's limits by exactly the amount quantum mechanics predicted. The universe genuinely supports instantaneous connections between distant particles. Bell's theorem forces us to abandon at least one fundamental assumption about reality. Either distant objects can instantly influence each other, violating locality, or particles don't have definite properties until observed, violating realism, or experimenters cannot freely choose which measurements to perform, violating free will. Most physicists have chosen to abandon realism rather than locality, accepting that properties don't exist before measurement. But this choice transforms physics from the study of objective reality into the exploration of subjective experiences. Scientists have discovered that under precise conditions, a neutron could travel through one arm of an interferometer, while its magnetic properties traveled through the other arm. This isn't just a measurement artifact. The effect has been demonstrated in multiple laboratories. The results consistently show spatial separation between the particle and its intrinsic properties. If particles can exist independently of their properties, then what exactly is a particle? Objects aren't collections of properties. They're temporary associations between phenomena that can separate and recombine in ways classical physics never imagined. Contextuality sounds technical, but its implications are pure nightmare fuel. The same quantum system can give completely different results for identical measurements, depending entirely on what other measurements you choose to perform alongside it. The properties themselves depend on the context of observation in ways that violate every assumption about objective reality. Measure an electron's spin along the vertical axis first, then along the horizontal axis, and you get one pair of results. Reverse the order, horizontal first, then vertical, and the results change. Not just the second measurement, but retroactively the first measurement as well. In contextual quantum systems, the very question of whether a particle has specific properties becomes meaningless. Properties exist only within the framework of particular measurement contexts, disappearing entirely when you change the experimental setup. Reality becomes conversational, emerging from the interaction between quantum systems and the devices designed to interrogate them. Hugh Everett proposed the most disturbing solution to quantum measurement problems by refusing to accept that wave function collapse happens at all. Instead, all possibilities occur simultaneously in separate branches of a continuously splitting multiverse. When you measure a quantum particle's spin, you don't force it to choose between clockwise and counterclockwise. Both outcomes happen. The universe branches into two parallel realities, one where you observe clockwise spin, another where you observe counterclockwise. Each version of you believes they witnessed the real result, unaware that countless other versions experience different outcomes in worlds they can never access. Every quantum event splits reality into multiple branches. You're constantly dividing into parallel versions that experience slightly different quantum outcomes, creating an exponentially expanding tree of alternate selves. Some branches contain versions of you that experience miraculous luck. Other branches hold versions tortured by quantum bad luck, cosmic rays that cause fatal cancers, random decay events that trigger catastrophic accidents. The mathematics suggests that most branches contain versions of you that die young due to quantum accidents. In a multiverse where every possible outcome occurs simultaneously, death becomes impossible from your own perspective, trapping consciousness in an eternal nightmare of increasingly improbable survival scenarios. The quantum suicide thought experiment begins with a gun connected to a quantum random number generator. Each time the trigger is pulled, a quantum measurement determines whether the gun fires or clicks empty. In the many worlds interpretation, every outcome happens in parallel branches, from your own subjective experience, you can only perceive branches where your consciousness continues to exist. The versions of you that die simply stop experiencing anything, while the surviving versions continue their stream of awareness. To yourself, you would appear immortal, always finding yourself in the unlikely branch where the gun failed to fire. The implications extend beyond deliberate suicide attempts to every form of mortality. In a quantum multiverse, there are always branches where cancer cells fail to metastasize, where heart attacks reverse themselves, where accidents miss by inches. From your subjective viewpoint, you should expect to find yourself in increasingly unlikely scenarios where death is avoided through quantum coincidences. But immortality in the quantum multiverse comes with a terrible price. The branches where you survive become increasingly bizarre. You might find yourself living far beyond natural lifespans, sustained by quantum healing processes that violate biological laws. At the deepest level of quantum mechanics lies a question that terrifies physicists. Does consciousness create reality, or does reality create consciousness? Some interpretations place consciousness at the center of quantum reality. The universe exists as a vast superposition of possibilities until conscious observers force it to choose specific outcomes. Your awareness literally creates the reality you experience by collapsing quantum states through the act of observation. If consciousness creates reality through quantum observation, then what happens to the universe when you're not paying attention? Do objects continue to exist while you sleep? When you look at the stars, are you creating ancient light that traveled for billions of years, or are you retroactively determining what was always there? The alternative is equally disturbing. If consciousness emerges from purely classical brain processes, then awareness becomes an illusion created by complex arrangements of unconscious matter. Your sense of being a unified experiencing self would be nothing more than quantum information processing in neural networks. The question remains unanswered, leaving us suspended between equally troubling possibilities. Either consciousness has supernatural powers over physical reality, or consciousness is an elaborate illusion created by unconscious quantum processes. The quantum world vanishes the moment it touches the classical world, but nobody understands why reality chooses to hide its fundamental strangeness from everyday experience. Decoherence explains how quantum superpositions naturally evolve into classical definiteness. When a quantum system interacts with its environment, air molecules, photons, electromagnetic fields, these interactions entangle the system with countless particles. The quantum information spreads across so many degrees of freedom that superposition becomes effectively invisible. This explains why we don't see quantum effects in everyday life. Your coffee mug doesn't exist in superposition because it's constantly interacting with air molecules, photons, and gravitational fields that entangle it with the environment. But decoherence doesn't actually solve the measurement problem. It explains why superposition becomes practically unobservable, but not why it becomes actually non-existent. If a quantum particle becomes entangled with a detector, which becomes entangled with a computer, which becomes entangled with a human observer, why doesn't the entire chain exist in superposition? Scientists have achieved quantum effects in increasingly large objects by carefully controlling their environments. Each success pushes the boundary between quantum and classical behavior further into the macroscopic world. But the mystery remains: why does reality seem to prefer classical definiteness over quantum superposition? Deep within the mathematics of physics lies a principle so fundamental that violating it would unravel the logical structure of reality itself. Information cannot be destroyed, only transformed or hidden in ways that make it practically irretrievable. Every process in quantum mechanics can theoretically be undone. Particles that scatter can be made to unscatter. Wave functions that spread can be refocused. This time reversibility requires that no information about the system's initial state ever truly disappears. If information truly cannot die, then nothing you experience ever completely disappears. Every moment of consciousness becomes a permanent addition to the universe's infinite memory. Every thought you've ever had, every decision you've made, every quantum measurement you've observed gets encoded as information in the universe's wave function. When you burn a book, the information doesn't vanish. It gets encoded in the precise arrangement of ash particles, the exact spectrum of light emitted during combustion, the thermal vibrations of air molecules heated by the fire. The information survives in scrambled form. Black holes devour information and seemingly destroy it forever, creating a paradox that threatens to tear apart the logical foundations of quantum mechanics and general relativity simultaneously. When matter falls into a black hole, it carries information, the precise quantum states of every particle. Classical general relativity suggests this information vanishes permanently once it crosses into the black hole's interior. But Stephen Hawking discovered that black holes emit thermal radiation due to quantum effects near the event horizon, slowly evaporating over astronomical timescales. Hawking radiation appears to be perfectly thermal, random energy with no information content whatsoever. If you throw a library into a black hole and wait for it to evaporate, the emerging radiation shows no trace of the books that fell inside. Information destruction violates quantum mechanics at the deepest level. If black holes permanently erase information, then quantum mechanics fails catastrophically for any system that contains or interacts with black holes. Recent theoretical work suggests that information might be preserved in black holes, but encoded in ways so subtle that it appears to be lost. Hawking radiation is not truly thermal. Quantum effects near the event horizon create correlations between outgoing radiation particles that encode precise information about everything the black hole ever consumed. The encoding mechanism involves quantum entanglement between particles falling into the black hole and particles that eventually emerge as Hawking radiation. The information doesn't emerge immediately. A photon that evaporates from a black hole today might carry quantum memories of matter that fell in millions of years ago. The fundamental equations of physics work equally well forward and backward through time. Yet the universe displays a clear arrow of time that breaks this symmetry in ways that suggest reality itself might be fundamentally lopsided. At the microscopic level, physical laws show perfect time symmetry. If you filmed an interaction between individual particles and played the movie backwards, the reverse sequence would obey exactly the same physical principles as the original. But macroscopic reality violates this symmetry completely. Eggs don't unbreak, smoke doesn't flow back into cigarettes, memories don't predict the past. Recent experiments have demonstrated quantum retrodiction, the ability to use quantum measurements to infer information about past quantum states. These experiments show that quantum mechanics genuinely works backwards through time with the same precision it works forwards. The most unsettling possibility is that time symmetry breaking emerges from consciousness itself. If conscious observers play a special role in quantum measurements, then awareness might be the phenomenon that distinguishes past from future. Quantum mechanics might allow genuine backward-in-time influences, where future measurements reach into the past to determine the very causes that led to those measurements, creating closed loops of causation that violate every assumption about temporal order. Consider a quantum delayed choice experiment stretched across astronomical distances. A photon from a distant galaxy passes a massive star that acts as a gravitational lens, creating two possible paths toward Earth. The photon's path choice doesn't just reveal which route it took, it actually determines which route it took during its billion-year journey through space. Some interpretations of quantum mechanics explicitly embrace retrocausality. Two-state vector formalism describes quantum systems using both past and future boundary conditions, allowing future measurements to influence past quantum states through backward-evolving wave functions. The most unsettling possibility is that consciousness itself operates through retrocausal quantum effects. If awareness involves quantum measurements in neural systems, then conscious experience might genuinely reach backward through time to influence the brain states that create consciousness. In the deepest laboratories studying quantum mechanics, particles have been observed arriving at their destinations before they finished leaving their starting points. Quantum tunneling normally describes how particles can pass through energy barriers that classical physics says should be impenetrable. But recent experiments have revealed something far more disturbing. When particles tunnel through barriers, the process appears to take negative time. Particles emerge from the barrier before they finished entering it. Scientists measure tunneling time by analyzing how long particles spend inside the barrier region. Quantum measurements consistently show that the transit time is not just zero, it's negative. Particles somehow complete their journey through the barrier before they fully commit to starting it. Multiple laboratories have confirmed the effect using different experimental techniques and various types of particles. Photons, electrons, and atoms all display negative transit times when tunneling through appropriately designed barriers. The most radical explanation involves genuine backward time travel at the quantum level. If particles can influence their own past through retrocausal quantum effects, then tunneling might involve particles that reach their destination and then reach backward through time to initiate their own departure. If consciousness causes quantum wave function collapse, and consciousness itself emerges from quantum processes in the brain, then reality faces an infinite regress that can only be resolved by some ultimate observer whose nature transcends the quantum systems it observes. The measurement problem creates a chain of quantum interdefinite experiential states. Some physicists propose that the ultimate observer must exist outside the quantum mechanical description of reality. Religious and philosophical interpretations suggest that consciousness might be non-physical, operating outside the quantum systems it observes. The many worlds interpretation offers a different resolution by eliminating wave function collapse entirely. The most disturbing possibility is that there is no ultimate observer, that reality consists of quantum systems observing each other in closed loops with no external foundation. The universe might be a self-referential system that creates its own meaning through circular dependencies between consciousness and quantum mechanics. The most frightening prospect in quantum mechanics isn't that these paradoxes are unsolvable. It's that they might all have simple, elegant solutions that reveal reality to be far stranger and more disturbing than even the paradoxes themselves suggest. Every quantum mystery points toward the same unsettling conclusion. The universe as we experience it might be an elaborate illusion created by conscious observation of deeper realities that operate according to principles we can barely imagine. If consciousness genuinely creates reality through observation, then the material universe becomes secondary to awareness itself. We wouldn't be biological entities that evolved in a physical universe. We would be conscious beings dreaming the illusion of materiality. If many worlds interpretation is correct, then our entire experienced reality represents just one infinitesimal thread in an infinite tapestry of parallel worlds. Every possible version of history exists simultaneously. Our sense of inhabiting a unique, special reality would be revealed as the deepest possible delusion. If quantum mechanics points toward digital physics, then reality might be computational rather than material. We could be information patterns running on some cosmic computer, experiencing the illusion of physical existence while actually consisting of nothing but data structures and algorithms. The most terrifying possibility is that solving quantum paradoxes reveals that existence itself is far more fragile than we imagine. If reality depends on conscious observation, then the universe might cease to exist if consciousness ever stopped observing it. Perhaps the real horror is that these paradoxes serve as protective mysteries that shield us from truths too devastating for human minds to accept. The confusion and uncertainty might be the universe's way of preventing conscious beings from discovering the ultimate nature of existence until they're psychologically prepared for revelations that would otherwise drive them insane. Scientists continue their investigations, driven by curiosity that might be leading toward discoveries that fundamentally alter human understanding of existence, consciousness, and reality itself. Each answered question reveals 10 new mysteries, as if the universe actively resists complete comprehension. The final paradox might be that quantum mechanics can never be fully solved, because the solution would require conscious observers to transcend consciousness itself, stepping outside their own awareness to observe the systems that create awareness. We stand at the threshold of ultimate understanding, terrified to cross.